In this section, we'll discuss the idea of limits. In a standard calculus course, this is one of the first objects you would study before you even get into defining the derivative. We'll find here that the limit is intimately related to the standard part, which is why we started this class with studying standard parts and infinitesimals. And we'll be able to use those concepts now to handle and describe limits. But we'll find that limits are very nice for capturing behavior of functions, in particular as the input gets infinitely large or infinitely small. So first things first, let's get a definition. So the L is the limit of f of x as x approaches c if whenever h is infinitely close to c but not equal to c, f of h is infinitely close to L. Okay, that's a mouthful, and we'll talk about, break this down what it means, but let's just talk about, here's the symbol for it, and we read this as the limit of what? Of f of x when as x approaches c is equal to L. Again, the limit of f of x as x approaches c is equal to L. Okay, so breaking down this definition, what we're really saying is that if h is infinitely close to c but not equal to c, then f of h is infinitely close to L. Well, how do we calculate it infinitely close? We do that with standard part. So the standard part of f of h is equal to L. So this is what we're saying in words, that if h is infinitely close, so if h right here is infinitely close to c, right? If it's infinitely close to c, that means the standard part of h is equal to c. So if h is infinitely close to c but not equal to it, and the standard part of f of h is equal to L, then the limit, as x approaches c of f of x is equal to that number L. Okay, so there's our definition. And now it would behoove us to look at some examples. So let's compute a limit. So let's say, what is the limit as, whoops, let me reset it. So what is the limit as, say, x approaches 2 of the function x squared minus 4 all divided by x minus 2. So we want to compute this limit. We want to know what is it equal to. And so what we do is we say, let's let h be infinitely close to 2, but h not equal to 2. And we want to know what is the standard part of this. So what is the, so this limit is equal to, if it exists, the standard part of h squared minus 4 divided by h minus 2. Well, if we look at this, the standard part of h is 2, the bottom would be 0, so we can't use our quotient rule here. But notice also if h is infinitely close to 2, this is 4 minus 4 is 0. So we've got 0 over 0. So this is an indefinite form, right? The top is an infinitesimal, infinitely close to 0. The bottom is an infinitesimal, infinitely close to 0. And so we need to do a little bit of algebra. No problem there. We've had lots of practice with standard parts. First things first, let's look at polynomials, so we should be able to factor it. And sure enough, it's h minus 2 times h plus 2, all divided by h minus 2. And look, we get some canceling out. right? Because the h minus 2 on the top, the h minus 2 on the bottom, so this cancels with that. And so this is equal to the standard part of simply h plus 2. And now h is infinitely close to 2, so this is equal to 2 plus 2, which is 4. And that's our limit. We could say that now we know that the limit as x approaches 2 of x squared minus 4 all divided by x minus 2 is equal to 4. As x gets infinitely close to 2, this ratio gets infinitely close to 4. Okay, let's try another example here. So we will mark this off and look at the limit of x approaching 0 of, say, the square root of x plus 1 minus 1 all divided by x. So if I want to compute this limit, what is it equal to? Well, over here, I'm going to let h be infinitely close to 0, but not equal to 0. So it's an infinitesimal. And this limit would be the standard part, provided it exists, the standard part of square root of h plus 1 minus 1 all over h. And if we were to just blindly try to use the quotient rule for standard parts, we see, oh, we'd be dividing by 0. But a double check, if we let h be infinitely close to 0, the numerator is also, the standard part of the numerator is also 0. So we've got an infinitesimal over infinitesimal. That's an indeterminate form, so there's a little bit of hope. So this is equal to, and we've had plenty of examples with radicals. We know what to do. The standard approach is we're going to multiply by the conjugate. So h plus 1 minus 1 times square root of h plus 1 plus 1, and that whole thing is divided by h times square root of h plus 1 plus 1, right? So I need a little bit more room. We're computing this standard part. We've used conjugation. We know how conjugation works. So the top, so we'll have the standard part, and the top, those squared. So I get h plus 1, and then we get a minus 1, all divided by h times the square root of h plus 1 plus 1. And we get some nice canceling because the 1 and the minus 1 here, this is a big fat 0. So they cancel out. And then all that's left in the numerator is an h, and we've got an h on the bottom and the top, so they cancel. And now this is simply equal to the standard part of 1 all over square root of h plus 1 plus 1. And the standard part of 1 is 1. The standard part of the bottom, well, remember h up here, this is why I wrote it. You should do this too, remind you what they are. So h is infinitely close to 0, so the standard part of h is 0, right? So standard part of h equals 0, and so this is 1 over root 1 plus 1, which is 1 over 1 plus 1, simply 1/2. So we now know that the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x is simply equal to 1/2. Again, as x gets infinitely close to 0, this ratio, this function, will get infinitely close to 1/2.